All right, guys, so let's get started. This chapter is about potential energy and energy conservation. Okay. So, if you have seen the fundamental theorem of calculus, this entire chapter is based on that. Okay. So, let me show you what that is. Okay, so you might have seen the fundamental theorem of calculus says if you're integrating a perfect derivative, so a to b, you guys saw that derivative integration and taking derivatives are inverses of each other. So if you take the integral of a derivative, then this is equal to, they undo each other, so this is fx in the limits a to b. So this is just that function evaluated at b minus that function evaluated at a. That's the fundamental theorem of calculus. Okay. So now we begin to use that. You guys remember we said if an object is moving along a straight line and if this force is, now don't confuse the notation, if this force is a function of x, the work done by this force is given by this integral. The work done by that force is given by the integral. Now, what if this force is a derivative of a function? And u is the symbol used. We'll come to that function in this function is called a potential energy function. Okay, and the negative sign, we'll come to that in a little bit. What if the function is given by that? These forces are special kinds of forces. They're called conservative forces. Okay. And for now, this semester, there's only two examples of them: spring force and gravity. Okay, so the question is the following. So if you want to calculate the work done by a force, okay, so you have to do this integral. Now, we did this integral for a couple of different forces. You saw the spring force, we did it for the bungee force and all that. Okay. For most of the forces, okay, so if this force can be written as the derivative of a scalar function, then let's see what happens. Do you have a question?
Yeah. Could you just explain that a little more conceptually?
Okay, so this is how you calculate the work done by a force that is changing with position. Okay. Now so this works all the time. Now we're considering the special case if this force is given by the derivative of a function.
Okay, so is that like a function of work then? So if we integrated that function of u of x, we would end up at fx.
Okay, so let's do that. So we're calculating the work done. Okay, so work done by a force that's dependent on the spatial coordinate is given by that. Now we ask, what if this force is given in that form? What if the force is like that? Okay, so let's calculate the work done. Okay, it's x initial to x final minus du x by dx. And again, remember, you can't do this for all forces. So for instance, the force that your car applies, it cannot be written like that. Friction forces cannot be written like that. When you're pushing on a Publix cart, you cannot write like that. Elon Musk's rockets applying forces, you can't write like this. Yep.
Why though?
What do you mean, why?
Why can't you write it like that?
Because the friction force depends on the weight of the object, it depends on the surfaces that are in contact. Drag forces depend on the speed, velocity of the object, and all that. So, in fact, only among the forces that you see, only spring force and gravity can be written like that. So, there are very few forces that can be written like that. But they're special enough where we devote an entire chapter to that. All right, so if a force can be written like this, okay, so now let's calculate the work done. Do you see any connection to the fundamental theorem of calculus? This is a derivative and that's an integral, inverses of each other. I'll bring the minus sign outside. Okay. Okay, these two operations are inverses of each other, so the integral is just u of x. There's the minus u of x and the limit. So the work done is negative of u x final minus so here's the thing, and that's the entire chapter. Okay. So if a force can be written like that, then the work done by that force can be easily calculated. All you do is evaluate this function at the final point and that function at the initial point. It's that easy. You don't have to worry about doing integrals. Okay? And we like it when life gets easy. Okay? This function is called the potential energy function. Okay. All right, so the punchline is the following. Again, now we'll go through the slides and, the way they write it in textbooks, it's hard to see all of this. And, okay, so if a force is conservative, that implies that so this is in 1D I'm talking about. The force can be written as the negative derivative of a function, and ux is called the potential energy function. Okay, and so the work done is minus u final minus u initial. That potential energy function evaluated at the final configuration minus the potential energy at the initial configuration.
Do you write that as u final plus u initial, or is like x separate negative?
Okay, yeah, the reason we write it like this is a quantity taken at the final point minus the quantity taken at the initial point. That is the change in value of the function. So that's why we like to write it like that. Okay, so work done is negative of the change in potential. Yep.
I know I keep asking this, but
Mhm.
what exactly is potential energy in this case?
Okay, so this object has potential. Okay, if it is moving, it has kinetic energy. And for conservative forces, gravity, you can associate potential energy with its configuration, with its position. It's called potential energy because you can release it whenever you want it.
I have a question then. So the two conservative forces we're dealing with
Mhm.
are spring and gravity, and
Right.
those are the ones with potential energies. Is that why they're the two we're working with? Like
I'm
when you
sorry?
back on the spring, it has potential energy when you let go of it, it
Mhm.
moves. And like you said, gravity's got potential energy. Is that why these are the ones that are the conservative forces? Because they
You can only associate potential energy with conservative forces.
What exactly is a conservative force?
If a force can be written like that, then it's a conservative force. Yeah, I'll be back. Hello?
It's just gonna take too long to build our God. I'm just fight out on my God. I'm taking classes and we haven't done these, so I understand that there's more years is good.
All right. So that is the definition of a conservative force. Okay, so now here's another thing that see, the work done just depends on the value of this function at the final point minus the value of that function at the initial point. Okay, so let me show you an example. So here's a mass attached to a spring, and as the mass moves, the spring exerts a force on it. All right, so let's say this is the initial position of the spring, of the mass, and here's a final position of the mass. Okay, so the spring is a conservative force, the spring force, and you can calculate the work done by the spring when it goes from here to there. Okay, so there is a formula. I'll give you the potential energy function for this. Okay, now let's see. What if I go from here to there and then back there? What is the work done? Same.
So it's fair to say that a conservative force is a force where position is the only factor, at least the only thing that really determines the amount of force is position.
Yeah, it depends on the position. Okay, so here's an important, this is how stuff is introduced. The work done by a conservative force, a force is conservative if the work done is independent of the path. See, if it was a friction force, that would depend on the path. Friction force would do, so if this was the path and this was the path, in the second path, friction force does more work. Okay? If it's your car, the car engine exerted more work, did more work on this path than this path. Okay? So if the work done depends on the path, then it's not a conservative force. Okay. All right, let me okay, so let me summarize this again. We are interested in calculating the work done by a force that is dependent on position. Okay, so that's the formula. Okay. Now, if this force happens, if you can write this force like so, then doing this integral is easy. Okay. This function is called the potential energy function. Okay, then this integral turns out, the work done turns out to be just that potential energy function evaluated at the final point minus the potential energy evaluated at the initial point. Okay? So for certain forces, certain special forces, calculating the work done is very easy. Okay? All right, and so I told you there's only two forces that we are going to talk about that are conservative. So spring forces and gravitational force. Okay. And for the spring force, the potential energy is given by 1/2 kx squared, and we'll show this to you in a little bit. And for gravity, okay, the gravitational potential energy just depends on the vertical coordinate, mgy. That's the gravitational potential energy. Okay. All right, so let's get into the slides. So now you see this, you understand this, work and potential energy. For certain forces, the work can be easily calculated using potential energy. Okay. Conservative and non-conservative forces. A conservative force can be written like so, and a non-conservative force cannot be written like so. What are the two forces that you'll know can be written like that? Spring and gravity. What are the forces that cannot be written like that? Everything else. Okay. All right. So here is so what was the other way of saying conservative force? What was the work? The work was independent of the path taken. Okay, so here's an example of this. Okay, so let's say this is a frictionless slide. Okay. Now, what are the forces of acting on this object? So the only two forces acting on this object will be gravity and the normal force if it's frictionless slide. How much work does the normal force do? 0. The only force that is doing work is gravity. Okay, so if this was a frictionless slide, you let go of this, it comes off at a speed here, and the fact that the work done by gravity is independent of the path, what that means is you can design the slide any way you want. It'll come, if this location is the same, it will come out at the same speed, no matter how the slide is designed. Okay, so that's an implication. Okay. Of course, you can't have any bumps that are higher than this, then it won't get there, but okay, so friction force is a non-conservative force, or if you're pushing this book, that's a non-conservative force. So the work you do will depend on what path you take. Okay, so non-conservative force, the work done is path dependent. Okay. So when only a conservative force acts, what we'll learn is that when an object moves, everywhere along the trajectory, the sum of kinetic energy plus potential energy is constant. Okay? This is called mechanical energy, and this is true when only conservative forces act. So in this case, again, the only two conservative forces you know are spring and gravity. So in this case, when only gravity is acting, what does that mean? That the drag force, air friction, is negligible. So when only conservative forces act, kinetic energy plus potential energy remains constant. So when you kick the ball, as the ball rises, it's slowing down, kinetic energy is decreasing, potential energy is increasing. But the sum of the two is always constant all along the path. Okay, so this fact helps you solve problems that you couldn't solve using just Newton's laws. Okay, it would be too complicated. For instance, here, if this is a frictionless path, the sum of potential and kinetic energy is constant, and you couldn't solve this problem, you couldn't find the speed there using Newton's laws. It would be too complicated. Okay, but using this fact, you can solve it. Okay. All right, so we just saw that the work done by a conservative force is just the negative of change in potential energy. Okay. So potential energy can be defined when dealing with conservative forces. Okay. How is the force related to the potential energy? Telling you something that we'll see again. Okay. Here's how the conservative force and the potential energy are related. All right, so the work done. So here in the slide we've written change in potential energy. I'll write it like so. Okay.
Going back to the previous idea, would it be fair to say that potential energy only exists when you're dealing with conservative forces?
Yeah.
Okay.
Mm-hmm. All right. So for conservative forces, the work done is change in potential energy. Work done is like that, and there's the change in potential energy. So this was for one dimension. For 3 dimension, this is a line integral, and we'll come to that later. But right now, most of the chapter will deal with forces in 1 dimension. Okay. So this slide shows you the derivation of gravitational potential energy. So the gravitational potential energy just depends on the vertical position of the object with reference to some reference level. Okay. So work done by gravity. So if you draw your x and y axis like this, the force of gravity on an object is in this direction. Okay. And the force of gravity is mg. The unit vector j is in that direction. And there's the unit vector I. And so the force is minus mgj. This force is there's the force. Okay. And what we've done here is we've used this equation. So the force dotted with the displacement, okay? And here's the displacement along the y-axis, dyj. J dot j is 1, and so the work done by gravity is minus mg dy y initial to y final minus mg, this is constant. Okay, so this is constant as long as you're close to the surface of the earth. Y initial to y final. Okay, so there's work done by gravity is minus mg y final minus mg y initial. And you see this is equal to u final minus u initial. So there is the expression for the potential energy. So gravitational potential energy is mgy. Okay. So the gravitational potential energy of an object of mass m close to the surface of the earth is mgy. Okay. Now, if you're flying to the moon, g is not constant as you go up. Okay. And so then we'll need a better expression. And we'll see in chapter 13, the better expression is g mm divided by m1, m2 divided by r. Okay. But that's a pain in the neck to use. So right now, we'll just be happy with this. So we won't let you jump more than 100 miles, okay? So if you're within 100 miles of the surface of the earth, this is good enough. Yeah. So here's the spring force. The work done by the spring force is negative change in potential energy. When you do this integral, that's equal to that. And so this is minus u final minus u initial. So the potential energy function is that 1/2 kx squared. So the spring potential energy is 1/2 kx squared. K is the spring constant. X is this when you stretch the spring or compress the spring. So if you stretch the spring by x or compress it by x, the energy stored is the same. Okay? And the stiffer the spring, the more energy you have stored. Okay? All right, we keep saying that a force is conservative if it can be written like so. Okay, and let me show you that for the spring force. There, the spring potential energy is that. And so, let's see, does it give the right expression for the spring force? 1/2 kx squared. And derivative of x squared is 2x minus kx. So you see this potential energy function does give you the right force. Okay. Okay, so conservation of mechanical energy. So let's say when you drop an object or you throw the object up and whatnot. Okay. So we'll consider the situation when only conservative forces act. So in this case, only gravity is acting. So what we're saying is drag forces are negligible. Okay, drag forces are friction forces. Okay, so the work done by gravity is change in, so the work kinetic energy theorem says this work done by all the forces acting on the object is equal to change in kinetic energy. And now if only gravity is acting, the work done by gravity can be calculated like so. That's equal to change in kinetic energy. That's minus mgy final minus mgy initial, equal to that. And so if you rearrange these terms, you bring that over here, final kinetic energy plus final potential energy is equal to initial kinetic energy plus initial potential energy. This is called mechanical energy, kinetic energy plus potential energy. Okay, so through the entire fall, the sum of these two terms is constant. So the sum of kinetic plus potential energy is constant. So here's what we are interested in. Here's this object as it's going up and down. What is happening? Its speed is changing and so on. The question is anything constant during that motion? And what we are saying is the mechanical energy is constant. Here's a more complicated situation. And that's a powerful statement. Here is a ball rolling down this slide. Its speed is changing quite a bit. And if it's frictionless, you ask the question, is anything constant? And now we're telling you that the sum of kinetic plus potential energy is constant. So that's a powerful statement. Yep.
So, what is mechanical energy?
Kinetic energy plus potential energy. Kinetic energy plus potential.
And yet, what does that actually mean? Like, what is it actually? I need more conceptual explanation of that explanation.
No, I don't have one. All right, so mechanical energy is kinetic energy plus potential energy. Okay? And this is conserved. When is it conserved? When only conservative forces act. Okay, so for instance, if friction is present, this won't be true. If you're pushing on it, it won't be true. If you're driving your car, that's not true. Yeah. So as far as you're concerned, only gravity and spring forces. Okay, so for instance here, so if this is a roller coaster and it's going on a frictionless path, okay, and it doesn't have a motor, okay, its potential energy plus kinetic energy is, the sum of those two is constant. Okay, so this yellow curve is mgh. Okay, it's the potential energy, and you can see the higher it is, the greater the potential energy. And this is the kinetic energy. Okay, so as it's climbing up, it's slowing down, and then once it starts losing its potential energy, its kinetic energy goes up. But the sum of those two at all points there, the sum of those two is constant. Okay. So this happens only in a frictionless case. So for instance, okay, so you can have a ball rolling down a hill. It has potential energy that gets converted to kinetic energy, potential, back and forth. And if there is no friction, this can go on, this will go on forever. And that would be a perpetual motion machine. Okay? Non-conservative forces. Okay, what's a non-conservative force? A force that cannot be written like so. Yeah. What are the examples? Friction, thrust, you pushing on an object, and so on. Okay. So when non-conservative forces act on a system, mechanical energy of the system changes. It is not conserved anymore. Okay. So when non-conservative forces act, you're changing the mechanical energy of the system. Okay. So change in mechanical energy is change in kinetic energy plus change in potential energy. So here's an example. Okay. If I lift this object up, the lifting force is a non-conservative force, and I've increased the mechanical energy of the system. Okay. And now if I let go and only gravity is acting, then in that motion, mechanical energy is conserved. Okay. So here are two non-conservative forces acting. You're pushing and there's friction force on this box. Okay. The work done by friction force is easy to calculate. The work done by friction force is minus F times D. Okay. So we saw that work done by non-conservative forces was, so in this case there were two forces acting, this and that. There's the other non-conservative forces, there's the friction force, and that's equal to change in mechanical energy. What does friction force do?
It slows you down.
So it does negative work. What it does is it converts mechanical energy. If it was moving, it's stopping the object. Well, where did that energy go? It got converted to heat. Okay, so it converts mechanical energy to heat. Okay, so if you bring that, it decreases. So that gets converted to heat. Okay. So the thermal energy of the system and the environment increases. I guess. Now, of course, we know that energy cannot be created or destroyed. So if you have an isolated system and if you can keep track of all the energies, which is hard to do, it's hard to keep. So for instance, okay, I pushed this object on there and this thing stopped. What happened to that energy? It got converted to heat, but I can't keep track of the heat. I couldn't measure the temperature change here and all that. Okay, and if I was smart enough to do that, I wouldn't be doing that. I'd be doing something else. Okay. All right, so for an isolated system, the change in mechanical energy plus the change in thermal energy plus change in internal energy, all the changes do add up to zero. That means if what that equation is saying is mechanical energy initial plus thermal plus internal energy in the initial configuration is this equal to in the final configuration. So if you're able to keep track of all forms of energy, okay, it'll remain constant for the system. The sum of all forms of energy is constant, and that's conservation of energy principle. Okay. Okay, so if you have a conservative, so what we have learned so far is if you have conservative forces acting on a system, then the force on a system at any location can be calculated by taking the derivative of the potential energy function. So what we are saying here is the behavior of a system can be deduced from the potential energy curve. So if you have this function, you know the force on the system at any location, and you can calculate the behavior of the system. So if you want to describe a system, all you have to do is give this curve, this function. And from there, you can calculate the behavior of the system. Okay? So for instance, for this spring, for this mass attached to the spring, okay, so if you pull it in this direction, this spring compresses, this stretches, and the system will get pushed back in this direction. If you push it in that direction, it'll get pushed back in this direction. Okay, the potential energy of this is given by this graph, this parabola. All right, so when the system is here, so let's say the system is here, there is the potential energy. You take du by dx is the slope of this line. Negative of the slope gives you the force. This slope is positive, negative tells you that the force on this system is in this direction. When the object is over here, there is the slope. The slope is negative, negative is positive. The force is in that direction. So if you have the potential energy curve, you can calculate if the system is here, you can calculate that the force is here. How about when it's here? Du by dx is 0. The force on it is 0. That position is an equilibrium position. Okay, so you see that the local minima or local maxima are equilibrium positions. Okay. So minima and maxima of potential energy curves are equilibrium positions. Local minima are stable equilibrium positions. Local maxima are unstable equilibrium positions. Okay, you saw that you can balance a pencil on its tip. That's an equilibrium position, except that that's an unstable equilibrium position. This is a stable equilibrium position. All right, so this shows you this derivation. It's so for a conservative force, the infinitesimal amount of work done is the force times the infinitesimal displacement, and that's equal to the small change in negative of the small change in potential energy. So Fx is minus du by dx. Okay, this is just a two-line derivation of how force and potential energy are related for conservative forces. Okay, so here's a potential energy curve. At this location, again, at any location, you go to the potential energy curve, calculate the force on the object would be just minus du by dx. Okay. Du by dx is 0 here. That's an equilibrium position, except that that's a maxima, a local maxima. That's unstable. Why is it unstable? Let's calculate the force at this point. At this point, du by dx is negative. Negative of negative is positive. The object would move in this direction. If it was here, du by dx is positive. Negative of that is negative. It would run away. So, if the object moves away from this location, it runs away. If you did the same thing here, you'll find that if you displace it there, du by dx is positive, negative or positive brings it back in this direction. If it was here, the forces would bring it back in this direction. So these are stable equilibrium points, and those are unstable equilibrium points. Okay, so this equation generalized to 3 dimensions is given by that. If your potential energy function is a function of 3 coordinates, then the force is negative of the gradient of this operator. Have you guys seen the gradient operator? Do you guys know what this means? All right. So I'll tell you quickly what the gradient operator means. So, okay, let's do a potential energy. Okay, so let's say I'm going to make up potential energy functions here. I'll just make up some numbers. This is 100 joules, 101 joules. I'm going to take another 5 minutes and finish this lecture. If somebody has to leave, you're welcome to leave. But okay, so let's say these are the potential energy functions. These are potential energy values. Okay. Now, so at different locations, the potential energy has these different values. Now, you can ask the following question, let's say, in what direction does the potential energy increase the fastest? Okay, so again, let me put in a couple of other numbers, 98, 97, 6. Okay, so you can see that the potential energy is increasing the fastest in this direction. Okay. And you can also say, let's say this is 1 centimeter, it's increasing 6 units per centimeter. Okay. That is what the gradient operator does. It tells you the rate of increase and the direction in which it's increasing the fastest. All right. So, U, X, Y, Z, I'm going to make up an example, x squared, y cubed, z to the power 4. So the gradient of U is defined like so. Del U by del X, that's partial derivative, plus del U by del Y, J, plus del U by del Z, K. Okay. Del U by del X is, what does this mean? You guys have done partial derivatives? No. Okay, so partial derivatives just means the following. Okay, so okay, so here is x, y, z. So partial derivative means how is u changing when you move parallel to the x-axis. Okay. Del u by del y means how is u changing when you're moving parallel to the y-axis. Del u by del z means what? I forget that one. Oh, well, there you go. So when you're moving parallel to the z-axis. Okay. How do you take these derivatives? Okay, you're treating the other variables as constant. Del u by del x just means you're taking derivative with respect to x, and the y and z are constant. Okay, so this is del u by del x is 2x y cubed z to the power 4 I. Okay, who wants to help me out with del u by del y? Okay. And that tells you the direction in which it's increasing the fastest. Okay. So for instance, why is this kind of information useful? So if this was a temperature function, gradient of the temperature tells you what direction the temperature is increasing the fastest, and heat flows in the opposite direction. Okay. So those functions are useful, and in this case, if it's a potential energy, the force is acting in the opposite direction. Okay. All right. So again, here's a potential energy function. This is a unstable equilibrium, stable equilibrium, and so on. So this is the potential energy function. This gives you the force at any location, and so on. Okay. So local minima are stable equilibrium positions. Local maxima are unstable equilibrium positions. Okay. Neutral equilibrium positions are where you have the potential energy curve is horizontal, and you can move the object, and you have a series of equilibrium positions. Okay, those are neutral equilibrium positions. Okay, so you see here is a potential energy curve for diatomic molecules. Okay, so this room is full of diatomic molecules, 2 oxygen atoms, 2 nitrogen atoms, and so on. So the question is, how far apart are these atoms? Okay, what this is telling you is, if they're this far apart, the potential energy is minimum. If you bring them this close together, the potential energy increases, and they're being pushed that way. If the 2 atoms are this far apart, the potential energy increased, and they're being pulled together. So you look at one potential and the potential energy curve, and you know the bond length. Okay. So again, this curve has all the information there is to. You can learn from this curve all the information you want about the system. Okay, so very important curve. All right, we will